Welcome to the third video in the Foundations of Computational Economics course. Today we will be talking about representing numbers on computers. We'll see everything inside of the computer has to be somehow represented with zeros and ones. And so all numbers, including the real numbers, which fill up the real number line, have to somehow be represented in binary format. This is done nicely with what's called floating point arithmetics, but because of this conversion, there is sometimes very surprising behavior that you would see, or you might see in your code. And therefore, understanding how computers work is an essential knowledge in computational economics. So let's look at that. Here's a very simple example. Even without knowing any programming, look here. In the first line, we have A to be assigned a number, 0.1, same with B and C. And then this third line checks whether the A plus B plus C does or does not equal to 0.3. So what do you think is the result of this test? I'll give you 10 seconds to think. Okay, let's run it. See, it's false. A plus B plus C does not equal 0.3. Why is that? Well, we'll find out today. But before we go into this, let's look at this interesting and simple code. Can we trust this calculation? So look, if interest rate is 4% and I'm going to be adding accumulated interest every day in a year, and say you invested $1,000 for 10 years, how do we calculate the accumulated amount afterwards? Well, we'll calculate this daily interest rate, and they apply it using a standard financial formula, right? The investment times the rate to the power, this double multiplication is a power of the number of periods. And we get some answer. In 10 years, we get almost $1,500. Can we trust this calculation? Well, now that we know that sometimes numbers don't work quite as we expected, maybe we should check. And so I've written this little piece of code. First, I'm just doing exactly the same as on the previous slide. We're setting interest. Here we're going to be adding interest accumulation even more often than per day, every hour. And this is going to be an investment for 100 years. Well, I want to see where there is any real difference. In the end, this amount computed using native computation is going to be printed. And then here's some additional piece of code which uses the module, the library in Python called decimal. Now this is specifically designed to take care of the inaccuracies we've looked at. And so you can actually prescribe the accuracy of calculation. And then essentially I'm doing the same thing and printing the amount and the sum. And the difference. So let's look at that. As you can see, the difference is the whole 14.78. Of course, this was a huge investment and for many years, and the interest accumulated very very often. But still, you do get sensible differences. Let's see why it happens. As you could have guessed, real numbers are simply represented with certain precision. And while doing calculations, these errors can accumulate and become large so that they may even have economic significance. In order to write robust code, we need to understand where these errors are coming from and how to write what's called numerically stable code. So let's first start with thinking about what we actually mean when we write numbers the way we do. So if r is a real number, and we write in what's called a base b, how do we do it? Well, imagine that we write digits, 10,358. So these numbers that I just wrote, they are different digits of the number r as we write it, and I can denote them d0 to dk. Now what we actually mean is that the number r can be represented as d0 of units, d1 of the basis b, d2 of the square of that base, and so forth. So for example, for decimal numbers where b equals 10, 7,631, that's 1 of units, 3 of tens, 6 of hundreds, and 7 of thousands. Notice here that the actual digits that we use, they go from 0 to up to a base, not including that. Right, otherwise it would not make sense to write the number as we do. Okay, so what about binary? So if b equals 2, then we only have two digits, 0 and 1. That's actually what we want in a computer. And then we work with numbers exactly in the same way. So writing 1, 0, 1, 0, 1, 1 actually means 1 of units, 2 of first power of the base, 0 of the second power of the base, 1 of the third power of the base, 0 of the fourth power of the base, and 1 of the fifth power of the base. So we can easily convert from binary number into the decimal numbers and vice versa. In fact, from any system to any system. So let's try to do another little example. For example, 1, 0, 1, 1 in base 2. What is that? Well, remember that these are units, these are twos, these are fourth, and these are eighth in base 2. And so I can simply write 1 of ones plus 1 of twos plus 1 of eighths, and that becomes 11. All right. Other common bases in computers are 8 and 16, where 16 is interesting because it needs additional digits, and the letters A to F are used for that. Now let's try to count together in binary. So the first number is 1. The second number is, it would be, it's impossible. If we add 1 to this one, then we would get 2, but 2 we don't have as a digit, so we have to go the next the next digit up. So it's going to be 1, 0. And this is 1, this is 2, 0 units and 1, 2. This is 3. This is 4, and so forth. I will leave this question for you to think about. Okay. Now let's think about how many digits we need to encode different values. In base 10, we need 1 digit to encode any number from 0 to 9, 2 digits to encode values up to 99, and so on. In base 2, we need 1 digit, similarly, to count up to 1, 2 digits to count to 1, 1, which is 3 in decimal, and so forth. In base 16, we need one digit to count up to 15. With the second digit, we can count up to FF, which is 255. And so you see that with larger bases, you can compact more values, decimal values, more values, into the number with lower number of digits. And that's essentially why they're used. Now, how about fractions? They work very similarly. So instead of taking positive powers of the base, we're taking negative powers of the base now, all the way up to some k, where k is the number of digits after the comma. And this is what we do in decimal in base 10 system, isn't it right? So 0.5 means that we take 5 of 10th, and 6 on the second place after the comma means that we take 6 of 100th, and so forth. And here's an example of how a third cannot be represented with a finite number of digits in base 10 system. Right, we all know that 0.333 and so forth, that's actually 1/3. And so 4/3 result in 1.3 repeated. Well, similar thing can happen in binary, of course. So let's take this example. Let's take this example very slowly. So let's look how to convert 1/10 into a binary fraction. We have 1/10, and we want to represent it as some number times 2 to some negative power, when we already have 1/10, so we'll have to multiply it with 2 to keep the equality correct. And let's try to get inside of this bracket something greater than 1. In principle, it could be between 0 and 1, but zeros are less interesting to write. And we'll start writing our answer here in binary. All right, so I think the power 4 will do. So we will get 16 over 10 times 2 to the minus 4. And that's, of course, 1, which is 2 to the minus 4, plus 6 over 10 to 2 to the minus 4. So this means, this here, means that we get a 1 on the 4th place in the binary. So 1, 2, 3, 4. And we can continue. How do we continue? Well, we take this, and now we can multiply by some power of 2. So multiply and divide by some power of 2, so that the number becomes greater than 1. And that's, of course, just 2. So we get 12 over 10, 2 to the minus 5th. And that becomes 2 to the minus 4 plus 2 to the minus 5th plus 2/10 to 2.1 to the minus 5th. Okay, so that means that on the 5th place we also have a 1. Wonderful. 2 to the minus 4 plus 2 to the minus 5 plus, now how much do we have to multiply? Also by 8, right? 2 to the 3rd. So that becomes 16. 10, and we've multiplied by 2 to the 8th, so to keep equality we have to add 3 powers to the negative 2. Now that's 8th place, and so 1, 2, 3, 4, 5, 6, 7, we get 1 in the 8th place in the answer. Okay, so we have 2 to the minus 4 plus 2 to the minus 5 plus 2 to the minus 8 plus what's left, 6 over 10 to minus 8. Now 6 over 10 we already had, right? So this is here. So the process will repeat itself. And from here we will start adding, next number, and we can already see that the pattern will continue. So that implies that 1/10 in decimal equals 00011 repeated in binary. And that's why 1/10 is impossible to represent exactly in binary. And that's the reason why the example that we started with was so. Because computer has to use a limited number of bits to represent any number, then this representation just has to be truncated somewhere, and that's how we lose accuracy. Well, let's look at this in a bit more detail. For that, we need scientific notation. Right? Scientific notation is a representation of any number as a mantissa coefficient, which is between 0 and the base of the number system, times this base to some exponent. And now we can represent this number and the exponent itself separately with some accuracy. This exponent, at least, can be integer, which is easy to represent using binary representation. Let me turn the fans off here. Okay. But that's how we get rounding error, because the number will have to be represented in a finite number of bits. So if p is the number of digits in representation of the coefficient, and exponent takes only so many bits, then it becomes bounded between some levels. And this representation of a number, which stems from scientific notation, then takes 1 plus pe of different digits and 1 bit for the sign. But because this number of digits is finite, and there are numbers which cannot be represented with a finite number of digits, as we just saw in binary, we start losing accuracy. The way the bits in the computer memory are organized to represent this floating point or approximate scientific notation, that can be different, and it differs by architecture. So in 32-bit computer, it's different than 64-bit computer, and it's not that important. But you can see that 1 bit is, in both cases, is given to represent the sign, and then so many bits to represent the integer, which has the exponent, and the rest of the space is devoted to representing the mantissa to a possible degree of accuracy, which of course will be limited. So instead of the real numbers, which cover the full number line without any breaks, the floating point numbers, which are worked with by computers, which is a computer representation of reals, it actually has gaps. And moreover, you can find the minimum and the maximum number that can be represented with a floating point for a given number of bits in the computer memory. And all the computations that we do, they have to be rounded towards the nearest representable number rather than the exact number. And so the example with 1/10 in the very beginning is the example of such approximation, of such rounding towards the nearest representable floating point. So rounding errors is one of the reasons that precision can be lost in the economic computation. And the main point to take away is that you cannot compare floats for exact equality. With integers, that's easier, with integer numbers, but we'll come back to that next week. There's also something called catastrophic cancellation. It happens that when you do an operation on two float numbers, which two numbers which only differ in some least significant digits, and then say you take a difference between two large numbers, and each of which is a representation, but if they differ by just a tiny amount, then this amount, the difference, will be essentially lost in the approximation. And then, of course, there's overflow and underflow. That's basically trying to represent a number which is too large or too small to be representable by floats. We'll look at some of these cases in the labs. As always, there are some further learning resources that you're welcome to see. You will be able to use these links in the notebook that will be downloadable.